So today we are looking at logic behind one of the most complex tasks in blast furnace, that is mastering its thermal control. Our goal is not just to maintain heat, it's to protect the physical and chemical architecture of the furnace to ensure a stable production. We will move from basic reduction chemistry to early warning system you use on every shift. To control the heat, we first have to understand the internal structure we are trying to protect. So, the living reactor anatomy. Think of the blast furnace as a living organism with the distinct zones. Look at the layers on the right. At the top, we have the lumpy zone followed by a cohesive zone where softening begins. Below that, dripping zone leads to the raceway, and finally the hearth where the metal collect. A healthy furnace relies on these distinct stable physical zones. Thermal control is at its heart about protecting this architecture. These architectures support a chemical journey that depends entirely on one thing at a time. So the descent of iron, reduction need time. Iron ore doesn't just melt, it has to be chemically stripped of its oxygen. Look at the reduction funnel in the center. We start with a hematite at the top, moving through magnetite and wustite before it reaches pure iron at the bottom. Notice the temperature gradient, it's a climb from 500 to 1100 degrees Celsius. Descent requires time. Ascending, reducing gases must have enough contact time with the ore to strip away oxygen efficiently. The fast descent compromises this vital contact. When that efficiency drops, the furnace energy balance flips from a heat engine to a heat drain. So the chemical engine, exothermic versus endothermic. So let's look at the thermal math of the furnaces. The engine is the raceway reaction carbon plus oxygen. It's exothermic, releasing a net amount of 2 to 2000 kilojoule. The drain is direct reduction where FeO react with solid carbon. Stability is a constant battle between raceway heat generation and the massive energy tax of direct reduction, which consume heat aggressively. When that energy tax becomes too high, we enter the dangerous state known as a racing furnace. Anatomy of a racing furnace. What does a thermal failure actually look like? On the left, you see normal descent, plenty of gas to ore contact, but on the right, in the racing thread, everything is moving too fast. Because the body descent too quick, unreduced FeO reaches the deep, high temperature zones. This forces massive amount of direct reduction deep in the furnace, sucking out heat you just generated. This creates a dangerous loop called solution loss. Now the head thief, solution loss. This is the viscous cycle of a cooling furnace. It starts with the accelerated descent which forces on reduced or lower. This triggers forced direct reduction in the hearth. Here is the paradox. A faster furnace becomes a colder furnace. Poor reduction starves the primary heat engine of its fuel because carbon that should have burned at the tuer is stolen by the solution loss reaction. To track this heat balance in the real time, we use the W metric. Now measuring the residual heat, W opening represent the quantifiable residual heat in the lower zone of the furnace. So it's a balance. Heat of combustion plus blast temperature minus heat of solution loss plus steam splitting and reduction. So data integrity note, if you see, if you if your top gas analysis is under maintenance, W calculation will be misleading and out of range. Don't make critical decisions based on the compromise calculation. Now let's look at our first major early warning sign. So the oxygen per ton hot metal factor. This is the math that can silently starve your process. Normally we assume a factor of 245, but if the furnace races and that factor drops to 235, your actual production rate spiked to 386 tons an hour. Because your coal flow is fixed, your actual coal rate dropped by 5 kg per ton hot metal. Can you see the problem? Racing silently starves the process of fuel, which only makes the cooling effect worse. To catch this spike early, you must watch your charging rates. And as for the charging rate, early warning system, you must value this is a most valuable tool on shift. It's RTR1 charging rate. So this compares actual charges to what we expect. Watch the triggers. It's a confirmed racing furnace if the 8-hour rate is 5% above the expected, or if the 4-hour rate is 9% above. A rapidly accelerating 4-hour rate is your earliest warning radar. Use it. When the furnace races, you will be tempted to just add more fire. But remember the golden rule, what it says. The furnace is not an incinerator. So, this is the most important mindset shift for an operator. Many think increasing PCI immediately generate heat. It doesn't. Initially, the furnace just burned coal instead of coke. The real mechanism of recovery is that a higher PCI rate eventually forces the burden to descend more slowly. Slower descent means more exposure to reducing gas and less heat sinking. Direct reduction deep in the hearth. You are controlling descent time, not just adding fire. To use that PCI lever effectively, we have to know its timing compared to steam. So the intervention, steam versus PCI, you have a fast lever and a slow lever. Steam acts quickly, controlling flame temperatures with a delay of 3 to 5 hours. PCI is your slow lever. It fundamentally alters the reduction ratio but takes 6 to 7 hours to fully affect metal quality. A 3-hour change in PCI is worth about 10 degree, but you would not see it for half a day. So let's visualize how these responses overlap. The thermal response. Time. This graph shows why chasing a temperature drop is so dangerous. Look at the blue peak, that's your steam response at 4 hour. Now look at orange peak, that's your PCI response way out at 11 hour. So chasing immediate temperature drop with Velena or PCI levers guarantee instability. You must time your intervention to match the delay to help you make these calls. We follow the operational decision matrix. Now, as far the operational decision matrix is concerned, this grid guides you action based on the furnace state and charging rate. So, if the furnace is hot but the charging rate is slow, increasing steam first, be very wary to offsetting coal variation below 5 for more than a few hours. And if you are building blast volume or the furnace is fast, do not set coal variation to negative. You need that fuel to fight the cooling of the fast descent. Finally, always remember to cross check your data. Data integrity and cross checking. A master operator never trusts a single instrument. If the top gas analyzer fails, your W calculation is compromised. If your W looks incorrect, Immediately cross check the analysis against the power station metric on the expert system trained. Always have a backup plan for your data. Let's bring it all together for the final takeaway. So, the mastery of thermal control. So, thermal control is not about reacting to the present, it is about broadening for the future. Remember our three pillars: anticipate the chemistry, a fast furnace breeds direct reduction, which starves the hearth of heat, monitor the pacing, use the 4-hour and 8-hour rates as your entry warning radar, time the lever, use steam for fast correction and PCI for the long term structural shift. Master the descent time and you master the furnace.